Our first goal is to review area between curves. So we'll start with a pretty simple problem to find the area between the curve y equals x squared and the x-axis from x equals 0 to x equals 2. Now, what the heck does that mean? Well, let's graph it. Y equals x squared. What we want to do is find the area under y equals x squared from x equals 0 to x equals 2. Now I'm going to do some fancy technical stuff which you don't have to worry about, but here goes. To show you what we're trying to find, I'm going to show you where that area is. From 0 to 2, that's what we're trying to find. How much area is in the blue? Well, let's take a look at what we're actually doing here. I'm going to take that out, and one more time. Find the area. Let me just start at 1 and go to 1 1/10. Okay, so what we're actually doing is we're going to take that region from x equals 0 to x equals 2 and divide it up into small rectangles. And by finding the area of each individual rectangle and then adding them all together, we'll have an approximation for the area under the curve. Well, you know from basic geometry that the area of a rectangle is length times width, or base times height. So the problem is, what's the height? Well, that's the problem since we already know the base is 1/10. Well, that was nice, 1/10. So the area of that little blue rectangle is length times width, which is 1/10 times the height. Well, the height is the distance from there to there. Well, if I were to ask you, how long is that segment? You would obviously say 2, because the y-coordinate of the top point is 3, and the y-coordinate of the bottom point is 1, so 3 minus 1 is 2. Likewise, on the little blue rectangle, the y-coordinate on the top is equal to the function x squared. So y equals x squared is the top point. The y-coordinate on the bottom is 0. So the height of the blue rectangle is x squared minus 0. So what we're going to do is add up all those little rectangles between 0 and 2 whose height is x squared minus 0. Now in order to do that, we're going to use a little calculus. So let's go back and take a look at the calculus behind this. So the calculus, we add up, that's the integral symbol, from 0 to 2, all the rectangles that have a height of x squared minus 0, and then the base of each rectangle is dx, which means the change in x, which is approaching 0. All right, now we're going to evaluate this. So this is the same as the integral from 0 to 2 of x squared dx, which is equal to x cubed over 3 from 0 to 2. Sub 2 in for x, and you get 8/3. Sub 0 in for x, obviously we get 0/3. And to find the value of the integral, we subtract those two. 8/3 minus 0/3 is 8/3, which is equal to the value of the integral, which is the area under the curve. Done. Alright, now let's take a look at a little bit different problem. Problem number 2, find the area between the curve y equals x squared minus 4x plus 3 and the x-axis from x equals 0 to x equals 3. Let's take a look at the graph. There's the graph of the parabola. Now we want to find the area from x equals 0 to x equals 3. So let me perform a little magic here and show you where that area is. from 0 to 3. There's the area. Okay, let's just go straight to the calculus portion of the computation. So here goes. Just like in the last problem, we're going to integrate from 0 to 3. X squared minus 4x plus 3 is the height of the curve. Each little rectangle. And then minus 0, which we don't need because the rectangle's hitting the x-axis and the dx. Alright, let's see what happens. Well, when we integrate this one, we get x cubed over 3 minus 4x squared over 2, which is 2x squared, plus 3x, 3, and 0 are the limits of integration. Subbing in 3, we get 27 thirds, which is 9, minus 2 times 3 squared, which is minus 18, plus 3 times 3, which is 9. Subbing 0 in, we get, guess what? 0. So 9 minus 18 plus 9 equals 0. Minus 0 is 0. Well, wait a minute. What the heck is going on? How can we have an area of 0? There is definitely blue area, which is not equal to 0. Well, the problem here is we cannot use the integral x squared minus 4x plus 3 for the entire area. And let me show you why. On the first portion of the area, when you're taking a look at that little rectangle, the top of that rectangle is the curve. X squared minus 4x plus 3. And then the bottom of the rectangle is 0. So the height is x squared minus 4x plus 3 minus 0. But when we get into this region, it's just the opposite. The top of the rectangle is 0 minus the bottom of the rectangle is the curve, which is x squared minus 4x plus 3. So the height of that rectangle in that region is a different value. So what we'll have to do back on the calculus page is split this area into two sections. We'll integrate from 0 to 1 using this height, and then from 1 to 3 using the second height. So let's see what kind of answer we get now. Alright, let me rewrite this. So we're going to integrate 0 to 1 of curve minus 0, that's the height of the first rectangular region, plus the integral from 1 to 3 on the top is 0 minus the curve. So the area is just actually going to become these two integrals combined together. Well, we already know what the first one is. It's x cubed over 3 because we just did it a minute ago, minus 2x squared plus 3x from 0 to 1. And then the second one, the only things that are going to change are signs, so we get negative x cubed over 3 plus 2x squared minus 3x, 3 and 1. Alright, let's evaluate these two integrals. Get a little room here. Alright, in this integral, subbing 1 in, we get 1/3 minus 2 plus 3. If we sub 0 in, we still get 0. So the first integral is equal to, well, we have 1 plus 1/3, or 4/3. So 4/3 is the area from 0 to 1. The second portion, if we sub in 3 into the second integral, which I'm underlining, we'll get negative 27 thirds plus 2 times 9, which is 18, minus 3 times 3, which is 9. Well, let's see what that adds up to. Well, that's negative 9. Negative 9 is negative 18 plus 18. That is 0. But now we have to sub 1 in. So putting 1 in there, we get negative 1/3 plus 2 minus 3, which equals, let's see, negative 1 minus 1/3 is negative 4/3. All right, 3 gave us a 0, 1 gave us a negative 4/3, and then you subtract those two values and we get 4/3. So what we've got for our final area, from 0 to 1, we have an area of 4/3. From 1 to 3, we have an area of 4/3. So the total area is 8/3. Well, let's go back to the graph for just a second. So each of the two blue areas has an area of 4/3, giving a total area of 8/3. All right, let's take a look at one more example of area between curves that's a little bit different, and that will be this one. Find the area between y equals x squared and y equals 2x. Well, let's not rely on the graphing program for this problem. Let's just kind of do this entirely by hand and think about it. So just a rough sketch, y equals x squared and y equals 2x. We're familiar with both of those graphs. X squared is our friendly parabola, and y equals 2x is a line that has a slope of 2 that passes through the origin, something like this. So the area we're trying to find in this case is this area between the two curves. Well, I'm going to blow that up a little bit so we can take a closer look at it. So it looks like this little sliver, like so. Now we're going to use the same technique, and that is we're going to examine this area as a series or a sum of individual rectangles. So looking at that one red rectangle, the only thing we have to figure out is the height of that rectangle. Well, again, the height is the y-coordinate of the top point and the y-coordinate of the bottom point, the difference of those two. Well, the y-coordinate of each one is the function value at each point. For example, that point is y equals 2x. And this point is y equals x squared. So the height of that rectangle is 2x minus x squared. So in order to find that area, we just have to sum together all those rectangles. So we use the integral to summate the height of the rectangle, 2x minus x squared, the width of the rectangle, dx. Now, since we're not using the graphing program, or we weren't given any more information, we have another problem to consider, and that is, where are we finding the area? Between what x coordinates? Well, it's from the left end point to the right end point, but what are those points? Well, in general, in order to find out those points, all you have to do is take the two equations, x squared being one equation, 2x being the other equation, set them equal to each other to find the 2 points of intersection. Well, simple enough. X squared minus 2x equals 0. Elementary factoring, yeah, we know. So the 2 points are x equals 0 and x equals 2. So we sub those in for our limits of integration, and we're good to go. At this point, all we have to do is evaluate this integral, and we'll have the area of the yellow portion. So, integrating 2x squared over 2, cancel, goodbye, minus x cubed over 3, limits of integration from 2 to 0 or 0 to 2. Subbing in 2, we get 4 minus 8 thirds. Subbing in 0, hey, guess what? 0. So 4 minus 8 thirds is 12 thirds minus 8 thirds, which is 4 thirds. Funny how that keeps popping up. 0. Subtract those two values. The total area is 4 thirds. And we are done. So you've seen 3 examples of the area between curves. And what we're going to do now is extend that to 3 dimensions, and we're going to find volumes of revolution. But that was just a little background to get us started, and we'll be ready to move forward from here. All right, very good.